I'd like to thank the organizers as well for giving me the opportunity to present this status update of the LIGO and Virgo gravitational wave detections. So let's see how this works. Okay, so this is our current gravitational wave detector network. It's composed of 3 detectors, the 2 LIGO detectors in the US and the Virgo detector in Italy. These are 4-kilometer size Fabry-Perot Michelson-Morley detectors with Fabry-Perot cavities. And we are slowly moving towards a global infrastructure of 5-kilometer size detectors. In addition to the 3 that I just mentioned, we will have in a few years' time 2 more detectors. Well, actually, one of them is already operational, which is the Charla detector in Japan. And then by 2024 or something like that, we will have a 5th detector in India, LIGO India. So as I mentioned, Charla was inaugurated on October 4, 2019, and the observations began on 25th of February 2020 with a modest sensitivity and binary neutral star range. This is a very interesting detector compared to the LIGO and Virgo detectors because it has new technologies in the sense that it is a cryogenic detector, so it's much more sensitive to intermediate frequencies than the LIGO and Virgo detectors, and it's also underground, which means that it's also more sensitive at low frequencies of the detectability range. So this slide here shows the LIGO Virgo current observing runs that have been performed so far, along with the range of detectability for binary neutral star mergers. So LIGO and Virgo have observed already during 3 runs, 01, 02, and 03. So the first run started in 2015, in September 12, 2015, and Virgo joined the second run on August 1st, 2017. This run ended on August 25, 2017. And the last run has been 03, which was originally planned to last for about a year, for 1 year, from April 1st, 2019 to April 30th, 2020. And the original plan was that Charla will join towards the end of this 03 run. So what you can see in the figure are the different time slots of any of these runs, together with the numbers that indicate the binary neutron star merger rate. Now, 04 is planned to start, if all goes well, on January 1st, 2022. But of course, the impact of the global pandemic, COVID-19, is not yet known. If everything goes well, those 04 will start on January 2022. But this is uncertain at the moment because of the impact of the pandemic. So 03 was originally designed to have two periods of observations with 6 months each, 03A and 03B, separated by 1 month in October 2019 of commissioning to upgrade the detectors. So 03B, as I mentioned before, was supposed to end on April 30th, 2020, but the run was suspended on March 27th, about a month earlier than originally planned due to the pandemic. So despite of this 1 less month of observation, 03 has been definitely a very successful run. What I'm showing here is the cumulative list of events and public alerts which have not been retracted. This means that they are of astrophysical origin during 01, 02, and 03. And as you can see in this figure, during 03, the number of detections increased significantly with respect to 01 and 02. During 01 and 02, the collaboration reported the detections of 10 binary black holes and 1 binary neutron star. And during 03, the detections have increased significantly, and we got an average of about 1 to 2 detections per week. So during 01 and 02, LIGO and Virgo revealed, gravitational wave astronomy revealed a new population of stellar mass black holes, which are significantly more massive than those which are inferred, those which are known from galactic observations of low mass X-ray binaries. So the total mass range of these detections by LIGO and Virgo of these black holes go from about 20 solar masses to about 85 solar masses or so. So this was one of the most important contributions of the first 2 runs to astronomy. In addition, during the second run, LIGO and Virgo detected the first binary neutron star merger ever observed, 1708-17. And this was an extremely important event because there were dozens of electromagnetic follow-up observations in all the range of the electromagnetic spectrum, and this somehow is considered to have started the field of multi-messenger astronomy. This detection, as you all know, has had a large impact in astrophysics, cosmology, and nuclear physics. Now we have a very clear association between binary neutron star mergers and short gamma ray bursts. This event has also given some support for the kilonova model and the synthesis of heavy element in the universe. It has also provided the first ever measurement of H0, the Hubble parameter, using gravitational wave information and redshift, using binary neutron star mergers as a standard science, luminous standard science. And then it has also provided constraints on the equation of a state of high density matter. This has been possible thanks to the analysis of the inspiral gravitational wave signal through the information encoded in the so-called tidal deformability parameter. Now, let me also mention about the inspiral range during O3. Let's move now to O3. This is the inspiral range of all three detectors during the second half of O3, O3b. These are the 21 weeks of O3b where data was taken. And you have here the inspiral range for binary neutron star mergers. So you have in blue the LIGO Livingston detector, which is the most sensitive detector of the network. Then in red, you have the Hanford detector. And in green and in purple, you have the Virgo detector. The specific numbers, you can see them on the bottom of the figure, and the message to take away is that all three detectors during O3b have been working at O3 design sensitivity or even better, in particular LIGO Livingston. So during O3, a major novelty with respect to O1 and O2 was the fact that low latency triggers, gravitational wave low latency triggers, were released as public alerts. So the rationale for doing this was to facilitate the rapid identification of counterparts, electromagnetic counterparts or neutrino counterparts to the gravitational wave detections, and also to maximize the science that the entire astronomical community or the entire scientific community could do with those gravitational wave detections. The way this worked was to release those triggers through circulars on the gamma ray coordination network. Here in the slide, I'm plotting two websites where you can find, if you are interested in those alerts, you can find the user guide for those alerts, and also the GRACE-DB, the gravitational wave candidate event database, where all these alerts, all of these triggers have been accumulated, have been listed. Okay, so the contents of the alerts for the astronomical community, in the case of compact binary coalescence sources, are listed in these slides. So the alert contains the false alarm rate estimate of the event candidate, the time of the event and the localization in the sky, a 3D sky map, the luminosity distance, and also classification of the source and properties of the source. So the classification is done using a quite simple method based on the masses of the individual components of the binary. So depending on the value of those masses, we inform in the circular if the system is a probable binary neutron star system, if it is a neutron star black hole system or a BBH system. And also if the masses of one of the components is between 3 solar masses and 5 solar masses, well, the system could be in this hypothetical mass gap range of masses where there's scarcity of known neutron stars and black holes. And among the properties of these alerts, of these circulars, we also have the probability. We also inform about the probability that one mass is consistent with a neutron star, and also the probability that the system ejects neutron star matter, which is very important for the kilonova model. Now, as I was saying before, O3 has been a very successful run, and in particular, as of today in low latency, we have 56 candidate events. Out of these 56 events, a few confirmed detections, which have been labeled as exceptional events, have already been published. These are 1904-12, 1904-25, and 1908-14. These are exceptional in the sense, exceptional events that have deserved their own single paper. They are exceptional events in the sense that they are detections that we didn't have during the first two observational campaigns. So let me briefly comment about these three exceptional events in the next slides. 1904-12 is exceptional because it was the first time that we were able to measure a BBH merger with asymmetric masses. So most of the detections during 01 and 02 were fairly equal mass binary black hole mergers. So this was a 3-detector observation with a network signal-to-noise ratio of 19, pretty high. So the masses of the components were 30 solar mass one of the black holes and 8 solar mass of the black hole. So this is a mass ratio of about 4:1. So the gravitational wave emission can be expanded on multiples, and the dominant emission, as you all know, is the quadrupolar emission, the L equals N equals 2 mode emission, the quadrupolar emission. But if the masses are asymmetric in the system, we can also have contribution of subdominant modes, higher modes, which are subdominant. In particular, the most dominant of these subdominant modes is the L equals N equals 3 mode. And indeed, with this observation, it was the first time that higher multiples, in particular the L equals M equals 3 mode, was observed. So in this figure, for instance, what you can see in this yellowish track, you can see the chirp, the evolution of the chirp mass in a spectrogram, which is associated with the L equals M equals 2 mode, with the quadrupolar mode. And the dashed line, a little bit on the left of this track, is the contribution of the L equals M equals 3 mode, this higher mode. Now, if you translate this into the frequency and you compute, into the energy associated with these modes, and you compute the energy, you can see that there is a non-negligible, a significant contribution of the L equals M equals 3 mode to the total energy of the system. Now, having these additional modes allows to carry on new tests of general relativity and to obtain further information on the source. The second detection, which is also very important for us from the point of view of astronomy, is 1904-25. This is exceptional because the final total mass of this system is 3.4 solar masses. So most likely this system corresponds to our second binary neutron star merger detected after 1708-17. However, there is no electromagnetic follow-up observation. This was mainly due to the fact that the sky localization of this event was very poor, because it was a 2-interferometer detection. So it was really, the source could be localized in the sky in a region of about, with an uncertainty of about 1,000 square degrees. So it was very poorly localized. So there is no electromagnetic counterpart for this system. So this means that the BBH, or the neutron star BH system, cannot be ruled out. Now, the important thing is about the total mass. The total mass of this system and the chirp mass of this system are much larger than any known system that we know so far in the galaxy. What I'm plotting here is a figure from the paper, where you can see on the left part, on the histogram and the fit, this is a fit to a normal distribution of the 10 galactic binary neutron star systems that are believed to merge within a Hubble time. And you can see that it peaks around, it has an average, around 2.6, 2.7 solar masses. Now, the peaks on the right, on orange and blue, they correspond to two different spin priors. Just focus on the red one, for instance. This peak corresponds to the total mass of 1904-25. And if you measure the standard deviation from the normal fit for the galactic BNS systems, you can see that it is 5 sigma away from the BNS systems known in the galaxy, which this may hint to perhaps the existence of a new populations of binary neutron star mergers, which is quite interesting. And the final event that I want to mention is 1908-14. This was publicly announced by the collaboration about 2 weeks ago. And this is important because it's the first time that we are not certain about what kind of object, what kind of object is one of the two components. For sure, we know that one of the objects is a black hole because it has a mass of 23 solar masses, but the other compact object has a mass of 2.6 solar masses. So the nature of the secondary component is uncertain. It could be a BBH or it could be a neutron star BH candidate. This was a 3-detector observation with a very high network signal-to-noise ratio of 25. And it is the source that we have localized best in the sky with an uncertainty of 18.5 square degrees, much better than 1708-17, but there is no electromagnetic counterpart. So an object of this mass, 2.6 solar masses, is compatible with a neutron star or a black hole, depending on the maximum mass supported by the neutron star equation of a state, which is currently unknown. So there's a lot of uncertainty in what the object could be. It is also important to mention that this is the system where the ratio of the asymmetry between the masses is the largest in all of our detections. It's a 9:1 mass ratio and asymmetry. So also higher modes are present in this particular investigation. Now, this system falls within the so-called mass gap. The system lies in the hypothesized lower mass gap between 2.5 and 5 solar masses between known neutron stars and black holes. So this mass gap is currently unknown. The existence of this mass gap is currently unknown, if it is real or if it is a selection bias. But most of the neutron stars and black holes that we know are not in this mass range. So this is also another reason why this system is particularly interesting. Now, talking about the future, to finish my talk, I would like just to say some words about the observing scenarios for gravitational wave detectors over the next decade. And for that, you should, if you're interested in that, you should look at this reference, this living review paper in Relativity, which provides information to the astronomy community to facilitate the planning for multi-messenger astronomy with gravitational waves. It touches on several sources, but it focuses primarily on the spiral of BNS systems, because these are the most promising targets for multi-messenger astronomy. And it's a paper which is periodically updated. So for 04 and 05, the BNS range of all 5 detectors, well, actually 4 detectors, not LIGO India is not listed here, but all 4 detectors are given here. So A+ is the upgrade of advanced LIGO for 04 and 05, and advanced Virgo Plus is the upgrade of advanced Virgo for 04 and 05. So during 05, A+ will observe with a sensibility with a range of 330 megaparsecs for BNS, and advanced Virgo Plus at best with 260 megaparsecs, and CAGRA with 140 megaparsecs. Now, if you translate those numbers into the number of events which are expected for 05, it gives an expected BNS detections of about 11 in the worst case scenario, and up to 180 detections per year in the best case scenario. Now, with a 4 or 5 site detector network working at design sensitivity, the gravitational wave signals will be localized to within a few square degrees for most sources. So during 01 and 02, the sources were very poorly localized in the sky, particularly at the beginning of the runs, where only the 2 LIGO detectors were observing. The addition of Virgo improved significantly this situation, because now we can triangulate the location of the source in the sky much better. But during 05, with both 5 detector network in operation, more than 60% of the sources are expected to be localized with an accuracy better than 20 square degrees. Now, for comparison, 17017 was detected with an uncertainty of 28 square degrees, and 19014 has been observed with an accuracy in the sky of 19 square degrees. Let me now jump to my conclusions. So the third science runs of the Advanced LIGO and Advanced Virgo detector network has recently finished, and all 3 detectors have been working at all 3 design sensitivities, or even better. The run, unfortunately, has to finish about 1 month earlier than originally planned due to the global pandemic, but nevertheless, it has been extremely successful, and it has yielded a record number of detections. During 03, for the first time since the Advanced LIGO and Advanced Virgo observation started, low latency alerts have been released publicly to the astronomical community. And this, in principle, was intended to facilitate follow-up observations by other telescopes and enhance the great potential of multi-messenger astronomy. So with this large number of detections in the pipeline, this record number of detections in the pipeline during 03, my advice for the astronomical community would be to please stay tuned for further news from the LBC camp in the next few weeks. And I'll be happy to take questions now. Thank you very much.
Thanks a lot, Tony, for this nice presentation. Actually, there are already 3 questions on the questions and answer channel. And if people want to put a few more, you're welcome. So if you want, you can read the question and answer yourself, or I can read the question as you wish, Tony. So this is the first one from Benjamin Montesinos.
Yes, since I am sharing the screen, I don't think I can see the question. Okay. So it's better if you read them for me.
Okay, Tony, I can read it. The first detections gave masses for black holes larger than those we knew from observations. And the detections involve neutron stars are also giving interesting numbers for the masses. Do you know if the theoretical efforts to accommodate these numbers into the stellar evolution theory are being successful?
Well, that's a very good question, Benjamin. So this is actually one of the most interesting questions to address in the near future. So far, we cannot really be certain if a stellar evolution can actually provide, for the case of neutron stars in particular, can actually provide those very high masses that LIGO and Virgo are detecting. So this is what makes actually these detections extremely interesting, because we may now have to revise our knowledge of stellar evolution. So my impression is that given the uncertainties that we have with the final states of massive the evolution of massive stars and with the supernova explosion mechanism, we cannot be certain if we can actually reach the masses that are being provided. And in addition to that, there are also additional more exotic proposals to accommodate those masses. So maybe those are not neutron stars, maybe those are not very light black holes, maybe those can be other type of objects like primordial black holes, or even objects which have been proposed within the fundamental physics community, like for instance boson stars, which could accommodate much larger masses being compact enough. So it's really now, I mean, during 01 and 02, the detections were, say, sufficiently simple to analyze. But now it's much more complicated because the detections are at borderline regions. So it's where we don't have really sufficient information so far, not only from astrophysics, but also for our waveform templates. For our waveform models have also to be improved in order to reach that region of the parameter space. So the excitement really starts now.
There is another question from Jose Bosch. From Jose Bosch saying, like, has there been a merge between a black hole and a neutron star? Do you think the gravitational wave and electromagnetic waves could interact in some way?
So the last one that I mentioned, this 1908-14, when the circular was released, it had a 99% probability that it was going to be a mixed system, a neutron star black hole binary. But now it's not so clear, so it is uncertain. And the reason why it's uncertain is because, in principle, the uncertainties on the equation of a state for it to be a neutron star, and also the fact that we don't have electromagnetic counterpart. And we don't have it could be a neutron star still if we don't have electromagnetic counterpart, because since the mass asymmetry is so large, so the black hole has a mass which is much larger than the other compact object. So the other compact object is just swallowed fully without any tidal disruption. So it could be a neutron star that is swallowed fully, and it doesn't radiate electromagnetically because there is no tidal deformation. But it could be a black hole on the other hand. So in any case, whatever it is, it could be the most massive neutron star that we know so far, or the lightest black hole that we have ever detected. And then there was the other, this was our most certain candidate for neutron star black hole binary, but we are not sure. We cannot really tell.
It could even be a quark star.
Yeah, it could be a quark star, a boson star. We don't know.
There is another question that I think you have answered, but I'll read it anyway. De Romano Corradi, que dice lo siguiente: entiendo que en O3 no se ha identificado ninguna contrapartida óptica de evento de onda gravitacional. ¿Cómo se piensa mejorar la identificación de las contrapartidas ópticas en un futuro de las fuentes, dado el escaso nudo éxito logrado en O3? O hay una reformulación de esta misma pregunta diciendo: ¿cómo se piensa mejorar la búsqueda de identificación de contrapartidas ópticas de eventos gravitacionales, vista pues la falta de éxito de que esta vez no ha habido suerte?
Yes, I was unsuccessful O3 in that regard. It was unsuccessful compared to O2, but I think that for 17 we were extremely lucky. the source was very close, and so I mean the galaxy was very close. It was a source which was easy to identify. I don't think that the way we are dealing with the electromagnetic follow-up observations and the way that this could be improved should be modified. I think it's just a matter of being lucky. For instance, this 1908-14, this has been observed with a very large scale localization, 18.5 square degrees. The problem is that the source is 6 times farther away than 1708-17, which means that the light is 6 squared, 36 times fainter. So even if there was an electromagnetic burst, it would be extremely, because this is a very compact emission, it would be extremely difficult to detect. So I think we need some amount of lag in order to detect those sources. They have to be closest. So as the detectors, of course, are being upgraded and we have much more reach, a much larger volume of the universe to observe and much more sensitivity, maybe things improve. But the approach that currently the LBC is following and the astronomical community as a whole is following for doing the follow-up observations, I think is sound enough, as was proved with 1708-17. In 03, we just have been unlucky that we didn't have a source so close.
Thanks a lot, Tony, for your presentation and for answering all these questions.